Hello, my name is Arezi Aki. This is my Lab 1 on constant velocity. The purpose of Lab 1 was to observe and analyze an object under constant velocity. The goal of this lab was to see if my predictions about the object's motion aligned with data both in my observation, which was charted through Tracker, and my calculations, which were measured in VPython. Here's a video showing the motion that I observed. So my initial prediction of motion was that the ball would move at constant velocity until some interaction with the ground would cause it to slow down and eventually come to a full stop. Similarly, the ball would have a tangible momentum until its velocity reached 0. Working in Tracker proved to be a little bit more difficult than I thought. As you can see, the line viewed in the graph to the left isn't exactly straight. Again, this is largely due to human error. I collected and selected the point masses as I went along, and as I was going along I noticed that the curve produced was very jagged. I found it difficult just to click on the center point, but I did try my best to do so. So using the information and the data provided in Tracker, I calculated the initial velocity of the soccer ball. And here you can see that I used the initial time, initial position, and then the second time and second position provided in the table in Tracker to calculate the velocity. And velocities change in position over time. So using the formula, I calculated that the initial velocity of the soccer ball was 0.364 meters per second. These are the lines that I changed in my VPython code. I took account for the mass of the soccer ball, the position of the ball, the velocity of the ball, using the initial position, of course, and then the initial calculated velocity. And then I changed delta t to 0.033 seconds, just for the sake of keeping things consistent. I changed the net force on the system to 0 as what was stated in the problem description. The velocity of the ball, I changed the formula as well as the position of the ball's formula to reflect Newton's second law. And then, of course, time was t plus delta t. So my model data versus experiment data kind of surprised me because it was staunchly different. So as you can see, there's a growing discrepancy between the observed and the model data. So there are a number of reasons why this could have happened. The clip that I selected for the experiment might not have been the best clip to use. The ball could have been speeding up during those frames, or slowing down, excuse me. Judging by the slope of the experimental curve, and this is what I think the error was largely due to, the point masses selected for the ball were inaccurate and too close together. It may have helped either to increase or to decrease the amount of frames. If I increased the amount of frames, I probably would have been able to get a larger, or just have a larger area to select from and have that straight line curve that I was looking for. Or if I had decreased the number of frames, the same thing. As you can see, kind of towards the beginning of the curve or towards like the latter half of the curve, you can see that the line is starting to appear to be more straight. And maybe if I had gone with those points, I would have produced a closer or more accurate data to pull from. And then currently, the graph is reading that the ball moves slower than Newton's second law of motion would dictate. And I thought that was interesting as well because from what I could see with my naked eye, I believed that was close to, if not constant, velocity. And the model that was calculated through VPython tells me otherwise. So I thought that was very interesting. In conclusion, I thought that Lab 1 was helpful in just getting a better understanding of what exactly constant velocity is supposed to look like in a graphical sense, especially when we're doing problems with the graph kind of telling us to analyze what kind of motion could be happening there. I did think that was helpful. So that is the end of my Lab 1. Thank you.